Hi, hello. Welcome to section. This is typically the least well attended section because everyone's just like, I just survived the exam. I don't want to go back. Um, but also, I try to build this section so that those who come, I think that we'll get done like maybe 3 challenge problems together today. So hopefully we can knock out a lot of the piece set, talk about the hard stuff, so it's a little bit easier and you have a little bit more of a break this weekend. Piece set 3 I think is only like 14 or 15 pages because it's only over 1 lecture. So that's good. But general game plan for today, I wanted to set aside the first like 10-ish minutes of section just for us to chat about the exam and kind of hear some of your thoughts about it and yeah, just like chat. And then the exam or section proper that we are going to do, there are basically kind of 4 big areas in lecture 5. There's amines and enamines, then there's the redox line reactions, CAD reactions writ large, and then the amino acid chemistry, which we did at the end. So if you have not already, go ahead and scan the QR code. The question for today is, what are your thoughts about the exam? And feel free to, because it's text, just be brief there, and then we can chat more here. But yeah, does anyone want to start us off with how did they feel about the exam? Also, apologize, I'm a bit low energy. I'm pretty tired. I was trying to get all of the exam graded in one day yesterday because I'm going out of town this weekend. And I got like 70% of it graded. And so I'm hoping I'll get the rest of it done today. Your grades probably will not be released until Monday because Logan wants to still go over it, and Logan's also out of town. So you'll probably get your grades back Monday night. But yeah, thoughts on the exam? Anyone want to share anything? And again, feel free to like speak your truth. Like, I wrote this exam, I put y'all through that, and there are some parts where like having graded it, I'm like, I think I did a little bit too much. So I would like genuine feedback. Yeah.
I didn't know what D was.
Um,
Is it hydrogen? Like?
yeah, it's the isotope of hydrogen. Yeah, it appeared in section.
No, I remember it. I wasn't sure.
Heard. What did you think was the worst question? Oh, yeah.
No, I was gonna say maybe it's like my fault for like just being like overwhelmed and not reading clearly, but I think like it was tough having things that we weren't really seeing, like having like 2 products, like for the one, do you know which number was that?
For the MO question.
Yeah, so I think like maybe that was my fault, because I just did what we've always done, just because I was like, I felt very
Well,
time constrained.
I think also people misunderstood what we meant by that. Like, with 2 products, I really were just meaning, like, for example, this is not the question, but if it was a Grignard reaction with a carbonyl, what we would want is the O- structure that's almost the alcohol and the MgBr+, which normally we don't care about. But for an MO question specifically, we want to keep track of all of the arrows, all of the products, especially when we're like predicting reactivity. And I think a lot of students interpreted that as like, oh, there's going to be a mixture of products or different things happening, when that's not what we wanted. And so I think that was something where like trying to clarify the directions of it would have been better. Yeah. And then you had a comment, right?
I think I was just gonna say that, like, I mean, I took all the practice exams in the 90 minutes, but then once you get to like the actual like room, which is so hard
It's
to like,
different.
keep track of time and like make sure you're not like spending too much time on one and then like
Yeah.
you skip a problem and like leaving enough time to go back. I think that's something that I just struggled with, was like making sure I had enough time to go back to the problems I like skipped over.
Totally. Yeah.
I think 2 things. One, like, I know in one of the practice exams we had like 2 mechanisms, and then on the other one there was 1.
Mhm.
So like I think for me personally, when I like got my exam and I was like, oh shoot, there's only 1. In my mind, that's automatically like, oh, like you either have to get the whole thing right or like, you know what I mean, like you're kind of cooked. Because like
Yeah.
when I took the one other exam, I think I got like the practice exam, I got half like the first one and then all the second one. So I was like, okay, like this is like, you know what I mean, like opportunity to like then get the majority of the
Yeah.
points on that one. So yeah, I think that like that scared me at first a little bit.
And
It's, like, taking-
can I say on that one, and I'll let you do your other point too. The mechanisms, the question where I think I had the largest misstep. So it's by far the hardest question on the test. I think it's also like, so I've graded all the mechanism. The mechanism is like significantly lower than it has been in the past. It typically always has like a less than 50% on it. But I think that the average was like 38% of the points. And it also, which I don't think is so much a read on y'all as much as like that mechanism was challenging because it did 3 mechanisms back to back. There were no weird steps in it. All of the steps were like straight up arrows from lecture. But I think it was just a little overwhelming to see those 3 reactions back to back of the conjugate addition with cyanide, like 1,4 addition of a CN, followed by reduction, followed by an acetal reaction. And like stacking all of those together, I saw like a lot of curved arrows where it seems like people clearly just kind of got stressed and then were just doing things to get to the product. And like we can only give you credit for arrows that match like what we have taught you how to respond. Like a lot of people were like having an O come around and attack a carbon and then kick off another carbon. Y'all have never seen that before. Y'all have only seen things attack pi stars, and you've seen like a lone pair push and kick something off. And so, yeah, it's kind of the thing where I wish we had, honestly, if I could redo it, what I would do is I would split that up and I would give you an intermediate in the middle. And I would say part A, get to this first intermediate, and then part B, do this like acetal stuff. And I think that would have been better. And so because of that, like I've asked Logan to go back and look at that question and be like, hey, can you take a pass at this and see where we can get more points? Because again, I don't think that this was the most fair. So apologies for that. Like that's on me. Yeah. And then you had one more point, right?
Oh, just like the arrow push page, I think that those like that's like normally a place where I like say times like I know I need like other places.
Yeah.
I think it was like the second step. I think
Second
we-
step's weird.
We like it was just like weird because I think like previously we've done that in multiple steps. You know what I mean? Like breaking and like reforming it. It was like and stuff. It was like weird. I don't know.
Specifically, that rearrangement is, or that reaction is a rearrangement, and it does this weird thing that you haven't seen before. It's one weird on the curved arrows, just based on the bonds made and broken, you should still be able to figure it out hypothetically, but that step was the worst step. Yeah, definitely. Yeah. And, yeah.
I just felt like, just as a reference to the time thing, I felt like I kept myself pretty on pace with what I was doing in the practice exams.
Yeah.
But it still took me substantially longer. I don't know like what specific set of problems or papers it was, but it took me significantly longer to get through the whole thing. And then like, again, made it so that I had less time. If, for example, I like started something, I was like, I don't know what's going on. And then I come back to it later, I just found myself being like, oh, like I only have a very little amount of time
I mean,
left. I don't know what the
honestly,
difference was, but it just felt
I feel like the mechanism was a big part of that because like that mechanism for y'all is not like a 10-minute mechanism anymore. Yeah, like it's the thing of even if you were kind of pacing yourself as you went along and let's say you had 35 minutes left for the last 3 pages, that mechanism is taking up 15 to 20 minutes of that 35. So yeah, you're going to be short on time. And so I really think that question was kind of the linchpin in it. The other one that was real rough was the resonance. The resonance was not meant to be that like crazy different. I think one of the traps of that question is we don't grade you on curved arrows for it. But in order to get the resonance structures, you need to be pushing arrows. If you're just moving a double bond over, I will say it is really, really, really common to do things that won't work. To make carbons with more than 8 electrons around them, to delete a carbon, to not have the right hybridizations, like a bunch of things. And so the resonance was harder. The box problems, I think, were easier than normal, which, again, feel free to disagree with that. And then some of the discerning stereoisomers and chirality, there were a few that were, like, tricky. Yeah. But other questions, other thoughts? Mm-hmm.
things didn't make the test like harder, but it was definitely like a shock factor a bit. But we started adding chlorines and the stereoisomers with nitrogen as stereocenter, and like it wasn't hard per se, but
When you say add chlorines, where?
like for the naming
Oh.
convention and that acid chlorine in the first.
Well, the acid chloride's a totally fair functional group.
And, yeah, I'm not saying
But-
it made the test harder, but I think like, and those aren't the only examples of like unique things in the test, but I feel like when you put also like D, for example, it didn't really affect the difficulty of the test, but I think when we saw that, it just kind of like
Through,
seemed
yeah.
to us.
I will say the nitrogen chirality, like that, people did very well on that. So that, like, it looks weird, and that's the whole point of it, to be like, do you know the definition of a stereoisomer of 4 different things attached, sp3 hybridization? But yeah, I can hear you. There was a lot of just like discomfort. Like we were presenting you with things that maybe is it within the, not maybe, things that you have seen before that's like parts of this course that are in some ways fair questions, but there's a lot of like shock value in how we kind of presented some of them that I think made it more challenging. Yeah. Yeah.
I think I was kind of expecting like the shock value to come from just the like reactions.
Mhm.
And so I think when I was like doing the easier stuff and there was like tricky stuff, I think I would spend more time on it and that like messed me up a little bit with timing, I guess.
Yeah. Heard.
The easy stuff felt a little harder than I was expecting.
Yeah. Especially like the resonance and the discerning stereoisomers, I think, were the trickiest of them. Yeah. Mm-hmm.
Do you know, like, kind of, like, do you think the average of this exam is, like, less than of, like, previous years having graded 70% of it, or is it still around the same?
I'm not sure yet, because we need to finish grading the individual. I need Logan to do a pass at some of the questions to see where we can give more points. Then we're doing the group, and then we're getting the composite, so then we'll see kind of where everything sits. But, like, if it's significantly lower than normal, we might, like, add points to everyone or just something. Like, we're not going to, like, make half the class fail, you know? Again, and also we care about you learning the material, you know? Go ahead.
Oh, yeah, I'm just curious, is this expected, like, after this weekend, we're sort of expected to be at the point where we're at 100 on this exam, if we, as going forward?
I would not say 100. I would say after this weekend, it would probably be the expectation that you're, like, at an 80%.
80? Okay.
Yeah. And, like, the thing that I will encourage you to think about your grade on this exam is that there are a few things where it's like the question that we did was kind of hard. Yes, and I will totally admit that. But very much, I think a lot of people get their exam scores in organic chemistry and they're like, wow, this is a reflection of me as a person, or whether or not I can do organic chemistry or be a doctor or a laundry list of things. And no, it's much more feedback on how your studying approach matches with how we are going to ask you questions. Because I will say the like format of how we are asking questions is kind of how we do questions here. Like there were a few that ended up being harder than we anticipated, but like all of the questions were, I would say, fair exam questions writ large. Again, there were some like wording things where I've been like, I think that was not great, but like all of them were ones where I think if they were spread out among different years or something like that, it would have been a little bit easier. But sometimes for some questions, especially for the reaction types, there are study methods going in that just are not working for reactions. And so the time between exam 1 and exam 2 is really a time to regroup and assess what is working and what is not for learning this type of question. So to help with that, like before the next exam, we're going to have 2 more how to study reactions little sessions where we're going to talk about like some other strategies for studying reactions and kind of putting them together. I also do mid-semester meetings with every student in the class. So in 2 weeks, the week before exam 2, like the entire week before exam 2, not exam 2 week, I'll send out like a calendar with like 12 hours of meeting slots, and I'll have students sign up for like 1 to 3 like 10-minute meeting slots, just so we can like touch base one-on-one about like, hey, how is studying going? What do you feel like is working or not working? Where you can ask like specific questions. Yeah. So that's all kind of coming up, but I'm hoping that like even if scores are a little bit lower than expected, it's not going to be like so discouraging that like actually we're all going to drop the class. Like I think that y'all are going to get through this and it's going to be fine. But yeah.
Could you just like maybe during this section or at the end, like, let us know if we're gonna go over the weekend and sort of review things like I don't know where we have to be at coming in next week. Just
I would say reactions. It's the last 3 pages of the exam. Because again, on exam 2, you're not going to have chairs, you're not going to have Newman projections, you're not going to have naming, you're not going to have functional groups, you're not, like almost all of the first 6 pages is not going to be on exam 2. Do you need to know MO theory in order to like do the rest of the course in reactions? Yeah. Do you need to know about resonance? Yeah, but like it's not going to be explicitly tested in the way reactions are. I think the next exam, it's going to be something closer to 6 pages reactions, 3 pages theory. So you'll have like 2 pages of box problems, 2 synthesis, and I think 2 mechanisms. Yeah. Any other last kind of questions or thoughts with exam things before we jump into section proper? I think my tone sounds kind of somber just because I'm like tired. I'm so sorry. Like literally I was up until like 2 grading and I fell asleep while doing laundry and then I like woke up at 7. I was like, and then I like accidentally ordered 2 lattes at Pavement. So this is my 2nd latte. When I like placed my little like mobile order. So hopefully we'll like get it together and we'll generate some enthusiasm for organic chemistry. Woo. But cool. Okay. Let's do a hard transition out of this into the first topic. So amines and enamines. These are going to be the functional groups and the reactions that are actually most similar to the acetal mechanisms of lecture 3. So before we kind of jump into the actual reactions, I want to go over some new functional groups. Remember, we're not going to like ask you explicitly for functional groups anymore, but it is our language of learning reactions. If you don't know functional groups, you won't be able to like see a reaction scheme and know what's going on. So you've seen a carbonyl before, which of course we have ketone, aldehyde, all the cats and everything. Another one that we talked about very briefly was a compound functional group called an enol, where we had an alkene and an alcohol. And why do we treat this as one functional group instead of 2? Yeah. Yeah, there's resonance between it. So because there's resonance between it, it reacts as one functional group. So if we take these and make them nitrogen, then our nitrogen version of a carbonyl is called an imine, I-M-I-N-E. And then our enol nitrogen version is called an enamine. Oh, enamine. So we also have a flashback for primary versus secondary amines, which we talked about in section 2. So a primary amine is a amine where there's only one carbon thing on the nitrogen. It doesn't matter if that carbon's primary, secondary, or tertiary. We call all of them primary amines if there's only one carbon on the nitrogen. And then we have a secondary amine where there are 2 carbons on the nitrogen. So we'll come to some of this other stuff as we get into the reactions. But let's look at the kind of core reactions for this, which is if we start off with a ketone or aldehyde, we can turn it into either an imine or an enamine based on adding an amine at a pH of about 5, slightly acidic. I think that we'll never make you write the pH around 5, but we'll sometimes include it on like problem sets and questions to kind of give you a hint tip off that this is the reaction that we are doing. So it's just mildly acidic. But the choice of whether we get an imine or an enamine depends on if we use a primary or secondary amine. If we use a primary amine, we wind up with an imine. And if we use a secondary amine, we wind up with an enamine. Already, all these functional groups sound the same, right? Amine, enamine, amine, amide. I'm so sorry. Like, that's just the names of them. It's really annoying. So the mechanism here, it starts off the same for both of these. Both of these are like 90% the same mechanism, and then they have one different final step. So to start off, our amine just straight up attacks the carbonyl. How is that different from the acetal mechanism? Yeah, we don't protonate it. Any reasons for why we can just straight up attack, we don't protonate? Slay. So a few reasons. One, nitrogen lone pair. Nitrogen's less electronegative, so its donor orbital is higher in energy. So one, we have a better nucleophile here with a nitrogen. Two, we're not in strong acid. We're not in H3O+, and so we don't have something acidic enough to protonate a carbonyl. We are in mild acid here, but if we were in strong acid, do you know what would actually happen? Like if we could protonate this, we would be so acidic that this nitrogen would also be protonated. And then it wouldn't have a lone pair and it couldn't attack. So we can't be too acidic and do this reaction. That's the kind of reasoning here. So because we have a better nucleophile, we can just straight up attack. We get to this tetrahedral intermediate, and then we do a proton transfer, which I think Logan wrote it as H+ transfer. You can also write it as proton transfer, PT. I like that because it's shorter. You have to write fewer words. Then when you do that, we get to this neutral intermediate here. So we've made this O- into OH, and then we've made the amine part neutral. And this functional group is called a hemiaminal. Now, where that comes from is an aminal is if we had two like nitrogens on it. We don't teach you really reactions with aminals here, but it's kind of like the amine version of an acetal, right? And a hemiaminal has an OH and an amine, kind of like halfway to an acetal is an OH and an OR. But I was in this building when I first heard this term. It was like my freshman year, and a TF in Chem 30 on the third floor here was doing this mechanism and said hemiaminal, to which my gut response was gesundheit, because that's not a word. That's like an involuntary utterance. That's something that like spilled out of your mouth that like is a little bit offensive. Hemiaminal, what are we doing? We've gotten a little high on our own supply. This is like chemistry nonsense at its highest, hemiaminal. At the same time, I'm saying it so many times because I do want you to know hemiaminal, because she is your goal like intermediate here. Why is she the intermediate that we see in the kind of highest concentration during this reaction? Any ideas, just looking at all these structures? Yeah. All the other intermediates have charges, and so they're going to be more transient. The hemiaminal is going to be the one where you can actually get like larger quantities in the intermediate, and also it's a good like bench point of like, can I make it to the hemiaminal? I'm halfway there. So we have hemiaminal as kind of a new functional group over here. And then once we get there, we do another protonation, because ultimately what we're trying to do is when we go from our ketone aldehyde to our amine or enamine, this O has left the building. So we have to take her first from an O- to an OH. We protonate her again to make her water, and then we can lone pair push her off. So when we do lone pair push, we get to this structure here. We have a CN double bond, but we have a positive charge. So we call that, so a CN double bond is an amine, but if it has a positive charge on it, it is called an iminium. And it's kind of like ammonia, ammonium. The IUM just means it's positively charged. She's more reactive than the normal amine. So this is where we differ. So this R here, if it's a primary amine, one of them is carbon and one is H. And if it's a secondary amine, they're both carbons. So this is where it splits off. A primary amine, we could make this neutral just by removing a hydrogen on it. And then we're at our amine, we're done. But a secondary amine, these are both carbons, and we cannot easily break a carbon-nitrogen bond. So what we have to do is this sneaky trick where we deprotonate here next door to the amine. So a little piece of nomenclature up here is if we have an imine or we have a carbonyl, we call the position next door to it the alpha carbon. And we call the hydrogens on them alpha hydrogens. I mentioned this when we were doing conjugate addition, because in the conjugate addition mechanism, we had a point where we had to push down and go grab a hydrogen at this alpha position. So that was an alpha protonation. But here what we are doing is we are doing an alpha deprotonation. So we are trying to get electrons up to this nitrogen. We are deprotonating at this alpha position and then pushing electrons all the way up to the nitrogen to get our neutral enamine product. So this notation, again, we're not going to test you on it, but it's useful to know these alpha beta terms are going to come back in lecture 6 and lecture 10. So like they are coming. But that is the imine and enamine reaction. Mostly the same, different last step. For the reverse reactions, because just like acetals, these are reversed, these are also about the same length of the acetal, so these are kind of a bit of a headache. For the reverse reaction, just like acetal, you use H3O+. Why do you need to use H3O+ for the reverse reaction rather than just H+? Look at the colors. Go ahead. Yeah, we need to add an oxygen, right? And the oxygen comes from, at a certain point in the reaction, a water needs to come in and attack. So it can't just be any old acid, it has to be H3O+ to provide a water to attack. And remember, whenever we have H3O+ in acid, we also have its conjugate base H2O present. You can write both of them, or you can just write one. So this is straight up, literally, the exact reverse of the Ford reaction. So I'm not going to go through it beat for beat. The only thing I will say is the first step is different for each of these, how we put back on a hydrogen. We either just do a straight up protonation at nitrogen or an alpha protonation. And then all the rest of the steps are the same. So to practice this, I'm going to start off with kind of a tricky example from the skill builders. For this is on page 8. This one looks a little crazy. So let's kind of talk about it together a little bit. Okay. So anytime we see a new reaction, what's the first thing that we should do? Functional groups, figure it out. So we have 2 aldehydes. Then what type of amine do we have here? Primary or secondary? Primary amine, because we only have 1 carbon attached to nitrogen. Great. And then, do you see any functional groups in the product? Because our product looks kind of weird. The product looks not like we expect it to. So, they're alkenes, but do they have resonance with anyone? With an amine. So what do we call an alkene and an amine together? An enamine. Yeah, our new one. And the thing that's kind of weird is we have a double enamine. It's an enamine on both sides. So that's kind of weird. The other thing that's kind of weird with our enamines is we started off with a primary amine. Does primary amines normally make enamines? No, primary amines normally make those imines, our CN double bonds. So we're doing some weird things. But if we just look at this so far, the only reaction that we know how to do with an aldehyde and a primary amine is to form an imine, I-M-I-N-E. So we are going to do some steps here, and I'm going to have you actually write out these steps. But the only thing that we know how to do is turn one of these carbonyls into a CN double bond. And is there anything else that should be on the N? The methyl that's on there. So we have this. And actually the step before, we're going to get to this aminium here. And so I'm going to have you just take a couple of minutes, not long, and just draw out the mechanism to get here. And then we'll figure it out from there together. And once you have this structure kind of written down, I would leave some space, have this structure in the middle, and then we'll kind of pick up that from the end. But once I give you like a few seconds to write this down, I'm going to switch back to the actual like mechanism from the notes so you can just see it. And it's literally copying arrows. It's the exact same like mechanism here, no weird steps. So do we have this one written down? Cool. So putting up the mechanism, here we are doing this one. So try it out on that to get to the intermediate.
Are you ever going to memorize the mechanisms or just line reactions?
For which reaction? For this one?
And reaction.
Yeah, you need both of them, definitely. Like, there are some reactions where we say are only line reactions y'all are responsible for, but like in general, you are learning the mechanism of the line reaction for everything. Yeah. Julia? Right. Andrea. Say again?
Both proton transfers to oxygen if there's two hydrogens on the Because here it's showing one.
So, one note about the proton transfer, which students often confuse. A lot of students want to go from this to this directly and just say proton transfer. But how many protons are moving if we do this? We would be adding 2 over here and removing 1 over here. That is not a proton transfer. Our proton transfer abbreviation is only for one deprotonation, one protonation together. And it's this idea of we are taking one off of one of them, putting one on the other. It's not a catch-all for any acid-base thing, you know? So we have to be very specific about only using the proton transfer when one's coming off, one's coming on. And then we do a separate protonation after it.
I was saying here, because there's 2 hydrogens on the nitrogen, we can do two leaving, 2 entering.
No. You can only do 1 enter, 1 leave for a proton transfer. And again, for this one, like even after you do this, like imagine this is primary, this would be an H and an R. You'd still have an H on it. Okay. So let's pick up from here. If you still haven't finished the amine mechanism here, that's one I think that you can do pretty easily later on your own, just because it's straight up the normal mechanism. But for now, let's try to analyze from here to the product now that we have an intermediate. So are there any carbons where you feel pretty certain that this carbon in the intermediate is mapped to this carbon in the product? Which carbon?
Whether with the residence with the oxygen,
This one?
the alpha carbons on oxygen.
These two? Which do you think they are in the product?
The ones that have, are alkenes and adjacent.
One or two?
One.
Work. Yeah, no, that works. That's the hardest way of doing it, in my opinion. There's a much easier anchor point. Does anyone see the easier anchor point?
Nitrogen?
Sure, the nitrogen. And the methyl to me is the one that stands out. Like there's only one methyl here. And so that has to be there. Right? Like y'all are all right. You all figure out anchor points, but I always like go with what looks the most obvious, what's most unlike everything else in the molecule. So if we have that, then we know that this nitrogen is this nitrogen totally. And then we get that this green must be one of those two greens up here. So I'm going to put it here. It doesn't matter. It's symmetric, so we can do either one. And then that would make this one over here, we skip to the other. So skip 2, and then we have the other. Okay, so we started to match carbons. And in particular, things that we need to do, we need to connect this nitrogen over here to this carbonyl, specifically to this carbon. So we need to do a connection there. And we're turning it into an enamine. So firstly, if this thing over here is going to like join a nitrogen and a carbonyl carbon, is there any world in which our carbonyl carbon is the nucleophile? She's always the electrophile, right? So we know that this needs to be the nucleophile. So in fact, what I'm going to do is I'm going to just make this the neutral protonation state. So imagine you did the amine mechanism and got to the totally neutral intermediate here, no positive charge. Well, if we think of this, instead of being our normal amine girl, we think of her as a nitrogen with 2 carbons attached to her. She looks kind of like a secondary amine, right? Like a little bit. It's weird because we have a double bond, but she has a lone pair, so she could attack, and she has 2 carbons on her. So our next step is going to be this nitrogen coming and attacking over here and pushing up. Now when we do this, we form a ring because this is intramolecular, and rings are tricky. Rings are really tricky to draw. So let me show you my favorite trick for this. What I would do is I would start numbering at the thing that attacks, and I would do 1, 2, 3, 4, 5. So I know I'm going to be making a 5-membered ring, and one of those things is a nitrogen, right? So what I do is I literally draw a 5-membered ring and make one of them nitrogen. I'm not thinking about mapping anything yet. I'm literally drawing a polygon. So then I do my numbering, 1, and it doesn't matter which way you go. 1, 2, 3, 4, 5, here, sure. And now what we do is at each of these, we make sure that we have all the things that we need to have on it. So on the nitrogen, we definitely need to have our methyl. Then on this 1 to 2, we need to have a double bond. Then 2, 3 is boring, 4 is boring. 5, we just attacked, and we used to have a carbonyl, but now what do we have after these arrows? Just an O with a negative charge, yeah. And this nitrogen up here would have a positive charge because it now has 4 bonds. So, okay, it looks like we're starting to get there. So from this intermediate, we have a lot of charges going on. So let's try to get to something neutral. First, let's neutralize this O minus here. And make it just a neutral OH. And then how do we alleviate the positive charge on a nitrogen with 4 bonds to carbon? What was our strategy that we did in the mechanism? We can't deprotonate at the nitrogen, so where do we deprotonate instead? See? At the alpha position. So this looks really weird, but this is our imine. One away over here is the alpha. So if this is our alpha position, we have something in the solution, grabbing a hydrogen, and then pushing up to the nitrogen. Well, that makes our first enamine. So we have enamine number 1 done. But then what functional group do we have over here where we have an amine and an OH attached to the same carbon? Bless you. Hemiaminal. So we have our halfway point in another amine-enamine mechanism. Okay, well, literally just looking at the steps, after we're at the hemiaminal, we're supposed to protonate the OH, lone pair push it off as water, and then we're at our aminium. So let's do those steps. So we are going to protonate this. I'm going to do, because it just says that we're in water, I'm just going to deprotonate water. So we're at our protonated water here, and then we lone pair push her off. So now we have an aminium on this side, and we are super duper close to this product. All we need to do is the final step of here, if we have a nitrogen with 4 carbon bonds, we're trying to alleviate that positive charge, where do we deprotonate? We deprotonate at the alpha position to this imine. So this is the imine, one away is the alpha position. And I'm just going to use Sol again. And that will take us to our product. So this one's a hard mechanism. This one's a hard mechanism because this transformation of making enamines and only have a primary amine is kind of out of left field. It's like looks really weird. And the crux of it is you had to stick to your guns initially and do the mechanism that you were taught of the imine mechanism. And then once you had an imine and a carbonyl together, the real key was seeing, hey, this kind of looks like a secondary amine, because now we have a nitrogen attached to 2 carbon things. From there, the other key point was spotting this hemiaminal and being like, okay, we can complete this. But do you see how a lot of our benchmarks were based on these new functional groups? Hemiaminal, amines, aminiums, knowing about like alpha protonations, deprotonations as steps. Like that's the language that we can use to talk about it. And until we have that language, it just feels kind of, we are doing mysterious arrows, you know? Any questions about this one? This one's a hard one. Yeah.
I don't know if you mentioned this, but why did you sum the other, like, why don't we have to, like, put a protective group on the other aldehyde? Like, why don't both
Oh,
of them?
this is not a protecting group.
Yeah, but why doesn't both of them, like, turn into, like, the nitrogen?
That's a great question. So hypothetically it could, right? But if you were to make it with both of them, before you get to both of them, you have to put on one, right? And so at this point, we have the option where an NMeH2 could come along and attack, or this one could come and attack, right? Why do you think this one's faster? The call's coming from inside the house, Brenda. Here, it is faster for a molecule to attack within itself than for another molecule to come and attack. Intramolecular reactions are almost always faster. Did you like that reference? Thank you, thank you. So intramolecular reactions are almost always faster than intermolecular reactions. That's a great question. And if we didn't give you the product, this would be impossible. Like there's no way for y'all to be able to predict what happens. A lot of what we are doing with these mechanism questions are wanting you to be like, can you explain what happened with all of this? But cool, I'm gonna keep chugging so that we can visit everything. So, I need a transition. So do you remember Gen Chem? Do you remember doing oxidation numbers? And you remember there was math and there were all these rules. Organic chemists are lazy. We say, that's too much. We only really care about carbon, organic chemistry. And since we only care about carbon, we need a shortcut rule for doing all of those like oxidation numbers and everything. And so we use oxidation levels, which is like baby oxidation numbers. So the shortcut is it's the number of bonds that carbon has to electronegative elements. I think Logan phrased this slightly differently in lecture, but like functionally we're talking about the same thing. We'll pretty much get the same answers, and we're not going to be testing you about the oxidation levels of things. So we see at the highest oxidation level 4, carbon has 4 bonds to things that are electronegative. So we have like CO2 and carbonic acid. And then oxidation level 3, we have a carboxylic acid and our other CADs. Oxidation level 2, we have ketone and aldehyde. And oxidation level 1, we have alcohol, and alkyl halide. So why do we use this? Why is this helpful? It's because things that are at the same oxidation level react similarly. I'm going to say that one more time. Molecules that are at the same oxidation level react in similar ways. So lecture 3 was all about oxidation level 2. It was reactions of ketones and aldehydes, right? And we saw that they did a lot of the same reactions. Like almost all the reactions that we could do in lecture 3 that started with a ketone could also start with an aldehyde. Lecture 5 was all about oxidation level 3. It's all about all these CAD derivatives and everything. Lectures 6 and 7 are going to be about oxidation level 1. So we're kind of doing a tour through all of these oxidation levels. And these oxidation levels are really helpful for figuring out how things react. The other thing is, okay, if we learn that these are all doing reactions at the same kind of level, these are all doing at the same kind of level, we need an elevator to go between floors of this massive kind of building of all the different oxidation levels. And the reactions that move between oxidation levels, we call redox reactions. So let's meet the players here. First, our main oxidizing agent is chromium trioxide, CrO3. That's the main one that we use for this course. There are a bunch of different oxidizing reagents. She always comes with a sidekick. So she's never alone. She's that girl that's always with a friend. Her sidekick is either water or it's pyridine, this like 6-membered ring with a nitrogen and a lone pair. This is a lot to write. So you can just write PYR for pyridine. And if you're trying to use a lone pair, PYR with a lone pair. That's totally fine. So she's our main oxidizing reagent. And then you know her, you love her, toxic masculinity, lithium aluminum hydride, our main reducing agent. You're already well equipped and have a lot of experience with her at this point. So they are going to be doing a lot of heavy lifting for us this semester, moving between oxidation levels. So one thing I'd like to do is I'd like to just take a moment to recognize them. Can we give them a round of applause? Thank you for your service. We appreciate you. Work. So we had this page in lecture that Logan spent all of like 3 minutes on, where he presented like 6 reactions, says, you don't need to know the mechanism, you're going to use these. I'm going to spend a little bit more time on them, but for most of these oxidation reduction mechanisms, they're just a little bit above the pay grade right now. You know, they're just a little bit hard because when we're doing reactions with chromium, she is a metal, she is of the earth, she's complicated. We're just not ready for those mechanisms right now. So we say, hey, y'all need to be able to move between floors of all these oxidation levels, but the mechanism is a bit too much. So what types of questions are these going to appear in if they're not in mechanisms? Box problems and? Yes, the line reactions are box problems. And then synthesis. Yes. So these are going to come up a lot in box problems and synthesis. So real quick, let's do an analysis of oxidation level. So if we start off on alcohols, what oxidation level are we at? 1 for all of them. Great.
Can the R be like negative or no?
No, we think of R as mostly carbon. Then aldehyde and ketone, what oxidation level are we at? 2. But what about carboxylic acid? 3. So these two, chromium, our oxidizer, is taking us up from oxidation level 1 to 2. But then it can also take us all the way up to oxidation level 3. But a couple of things to note. 1, if we're going from 1 to 2, who's our sidekick? Pyridine. But if we need to go all the way to 3, our sidekick has to be water. Does anyone want to take a stab at why it has to be water? Why do we need water? To add another oxygen, because we're going from one oxygen in the initial one to another one over here, we need a source of oxygen, and these oxygens don't leave chromium. Chromium has tight control over her oxygens. So with that, the other thing I want to note is that you can oxidize primary and secondary alcohols to an aldehyde. And I'm not going to give you a real mechanism, but I'm going to give you a fake mechanism. Chromium gobbles up hydrogens and then makes a double bond. Gobbles up hydrogen, makes a double bond. Gobbles up hydrogen, makes a double bond, and this one adds an OH. So why can we only do this with primary alcohols and secondary alcohols, but not tertiary alcohols? Why can't we oxidize this? So primary alcohols, totally fine to use chromium and oxidize it. Secondary, totally fine. Are there any hydrogens on this carbon for the tertiary alcohol for chromium to like gobble up? No, so we can't oxidize her. Similarly, if we need to go all the way to oxidation level 3, we can only have a primary alcohol. If we tried to do this for a secondary alcohol, do you see how we would have to break one of our bonds to carbon? We can't do that. That's hard. So we can only do primary alcohols all the way to carboxylic acids. One thing that was kind of mentioned implicitly is along the way to go from alcohol to carboxylic acid, primary alcohol to carboxylic acid, we actually form an aldehyde in the middle. So one thing that you could do is you could just go from an aldehyde to a carboxylic acid with CrO3H2O. Like that totally works. It would basically just be like starting at an intermediate in this reaction that we gave you. So know that if you need to take a aldehyde to a carboxylic acid, you totally can using our strong oxidizer chromium with its sidekick water. For the reductions, here, the 3 new ones we learned are going from carboxylic acid, amide, and nitrile, which are all at oxidation level 3. And lithium aluminum hydride, strong boy, toxic masculinity, takes us always to oxidation level 1 for all of these. So we are always adding for these reductions of a CAD compound here. We're always adding 2 hydrogens and going down from oxidation level 3 all the way to 1. You can think about it kind of like double addition to ester, but that one is one that you are responsible for the mechanism. These you are not. Cool. The last thing I want to flag on these is other than like the imine, enamine, like if you were doing imine, enamine hydrolysis, which is kind of rare-ish, These are the only reactions in the entire course that we are going to teach you where the product is an amine. This is all it can be. Like, there are no more reactions that we teach you for the rest of the course that makes amines. So if you see an amine in the product of a box problem or synthesis or something, you know that that either came from a nitrile or it came from an amide. And specifically, nitriles, they only make primary amines. So when we give you an amine, it's like, oh, okay, of all the sea of reactions we're teaching you, there are only a couple that it could be. So let's put these into practice here. So I've gathered these in practice number 2. These are pulled from page 6 and page 11, which are some challenge problems. But all of these box problems involve these redox line reactions. So take a few minutes and try out some of these. Remember, starting with your functional group analysis. And I would say also when you're doing your functional group analysis, thinking about oxidation levels and brainstorming the reactions that you know connected to these functional groups. Let's talk through these. So, starting up, what functional group do we have in our starting material? Ester. In our product? Carboxylic acids, and we have 2 of those, right? Well, we're thinking about redox land. How can we make a carboxylic acid? From what? Alcohols, primary alcohols. So let's imagine we had primary alcohols at both of these spots. And this is 1, 2, 3, 4 carbons. 1, 2, 3, 4. Okay, so here we have 1, 2, 3, 4 carbons, and we're an ester, oxidation level 3. And we're trying to get to alcohols, which are oxidation level 1. So, do we need to do an oxidation or reduction here? Reduction. So, let's start off with lithium aluminum hydride. And this double addition to ester, you know this mechanism actually. Going from here to here, this is, we add one equivalent of the hydride, we lone pair push, reform a carbonyl, add another equivalent, and then do an acid workup. So we've oxidized it to alcohols, and then, we've reduced it to alcohols. And then, how do we get from oxidation level 1 to oxidation level 3? We're definitely using our chromium oxidation agent. But what sidekick should chromium have if we're going all the way to oxidation level 3? Water. Great. Cool. For the second one, we're starting an alcohol, which is oxidation level 1, and we're going to an acetal. What oxidation level is an acetal at? Number of bonds that the carbon has to electronegative things. 2. It was with all of our oxidation level 2 things in lecture 3. Okay, you only know one reaction that makes acetal, right? So this came from, if we do our cut, a carbonyl plus an alcohol. So this is kind of what I mean about the exam 1 stuff that we want you to be proficient at now, of like, that should be an easy transformation that you're not having to think a lot about. Okay, well, this one is the one that looks more like our starting material, right? So how do we get from our starting material alcohol to this ketone? Did we do an oxidation or a reduction? We went from oxidation level 1 to oxidation level 2, so we go up floors, that's an oxidation. So we use CrO3, but if we're stopping at oxidation level 2, what sidekick do we use? We use our pyridine, yeah, exactly. So that is going to take us to this bad boy. And then, to get our acetal, we need to supply that alcohol with some H+. And here we can see how these redox reactions are interacting with some of the reactions we've already learned from lecture 3. Okay, lastly, we have a primary alcohol here. And then what functional group do we have in our product? It's one of the mean one land, but which one specifically do we have? We have an alkene and an amine, so together they are an enamine. Great. So with our primary alcohol to enamine, we can't do that directly, but enamines, we only know one reaction that makes them, right? So let's do a disconnection here. So enamines are kind of weird with their disconnection. I think amines are a little bit easier. But what we are going to do for the enamine reaction, like disconnection, is we are going to find the CN single bond where we are attached to that double bond. We chop off the nitrogen stuff completely. That's our amine. All we have to do is add an H on it. But then, what do we need to do to this bottom bit to make our original starting material? We need to pave over that double bond, make it a single bond, and then add a carbonyl. Again, fake mechanism of just how do we draw it. So let's try it out here. Okay, I find the carbon here that's connected to the double bond and the nitrogen, and I'm just going to straight up cut off the nitrogen part. So that's a 5-membered ring with a nitrogen here, and I've added a hydrogen on. And then on the other side, what I'm going to do is I'm going to pave over the double bond, make it just a single bond, and add a carbonyl to it. That's our disconnection. And here, this looks a little wonky, but remember, there's a hydrogen here. So this is just a normal aldehyde. Okay, so does this alcohol seem more like it's this going to become this carbonyl, or more like it's going to become this amine? The carbonyl, right? This alcohol is at oxidation level 1. This is at oxidation level what for the aldehyde? 2. So we use chromium to do an oxidation, and then which sidekick? Pyridine. Great. Just because we're stopping at 2. Okay, so that will take us here. And then we need to supply our amine. And then we might write our pH of about 5, but you don't have to. And that should take us there to make our enamine. So do you see how kind of when we're doing redox, there's a little algorithm for it of like, are we going up or down oxidation level? Okay, if we're going up, we're doing oxidation. What sidekick do we need for our chromium? And also, again, all of these redox reactions are going to interface with all the other reactions that we've seen. It's just moving between levels of the lecture like 3 reactions and lecture 5 reactions and everything. Cool. Yeah.
Do we need H3O plus for the last one? Or just a
For H3O plus for which one?
the bottom one?
For this, like
Yeah.
pH, no. Because remember, H3O plus is so acidic that it would protonate the carbonyl, and it would have protonated our amine, so it wouldn't attack. We'd have no reaction. Again, we want it to be like very mild acid conditions, like only just a little sprinkling of acid, not whole acid. Cool. So let's go on. CAD land, carboxylic acid derivative, CADs. CAD land is a magical place. It's like Oz. You know, there's so much going on. There's the Emerald City. There is all the other places in Oz. So a few things. We need to know the different functional groups in CADs. And specifically, one of the like core important facts you need to know is you need to know which CADs are more reactive versus less reactive than each other. I've typeset this, which is basically a page or two from lecture notes, and I've just tried to make it a ossified chart for you. But the core idea here is you need to know that acid chloride is the most reactive CAD that we have, followed by our anhydride, which we're not going to do many reactions of, but you could be asked a theory question about reactivity of CADs. Then we have our ester and carboxylic acid, which are pretty equal in reactivity. Our amides, which are lower in reactivity, our nitrile, which is kind of the lowest in reactivity that we actually do reactions with, and then the carboxylate's not very reactive at all. The explanation for why, spend some time when you're studying to go through these, but essentially they all have to do with resonance. When something has a more stable resonance structure, it's going to make the carbonyl less reactive. So like a carboxylate, we have equal resonance structures. They are equally stable. So it is the least reactive of all of them. Whereas up here, acid chloride has a horrible resonance structure because chlorine is huge. It's on a different row of the periodic table. And then the carbon is small. So they have really poor overlap. And then also you're putting a positive charge on a halide. They hate that. They are not here for that. So make sure you kind of understand the resonance arguments for why they are these different levels of reactivity. But the real big thing that we are doing with CAD reactions is we are just trying to interconvert between them. And there are kind of a few general principles. Logan gave you this information in a chart. I think webs are way more useful. I don't think in chart. I'm a spreadsheet girl, which is surprising that I don't think in chart for reactions, but to me it's so visual a skill. So what I've tried to do here is I have the functional groups listed in order of increasing reactivity here. So acid chloride's most reactive, it's at the top. Nitrile is least reactive of the ones that you've learned reactions for, so it's at the bottom. And it kind of goes up this way. And there are 2 organizing principles between all these interconversions. The first one is everything can become a carboxylic acid. The carboxylic acid functional group is the Grand Central Station. It's the Moynihan train hall, where any of these functional groups can be turned into a carboxylic acid. And generally, a carboxylic acid can be turned into any of the other ones, the exception being a nitrile. You don't know how to go from carboxylic acid to nitrile. So Grand Central carboxylic acid, she's the main character. She is the center of the friend group. She thinks that she's the main character because she is. The other kind of key idea here is you can always go down in reactivity in one reaction, but you can't go up in reactivity in one reaction unless you go through a carboxylic acid. So looking at this, acid chloride, you can go directly to ester, directly to amide, and we don't teach you when to go to nitrile. Hypothetically, she can. But you can go down in reactivity, super easy. But ester to acid chloride, there's no reaction for that listed here. What you have to do is you have to go to Grand Central to a carboxylic acid, and then carboxylic acid go all the way up to acid chloride. So again, if you're going down in reactivity, you can typically do it in one step. If you're going up in reactivity, like if you're trying to go from an amide to an acid chloride, then you typically have to go through a CAD first to get there. I almost like think of this as like a little board game of like, you're right here and I'm trying to go here. How would I do it? I just like take these little paths. So the thing with this, these mechanisms you are responsible for. I think a really good one to know solid is the Fischer esterification. I feel like that's a really representative CAD reaction. But remember Logan was like kind of dissing the arrows of this. I mean, like, aren't these easy at this point? You've done so many acid base, so many like attacking and carbonyl, so many lone pair push. You do want to get to where they're pretty easy, but these reactions, we see them a lot in line reactions and synthesis. So you are responsible for the mechanism, but I don't think that they're your most likely mechanism for like a full page mechanism question. They could be, you know, I don't want to like lead you astray, and I have not written the exam, but I would say these appear much more often, box problems and synthesis. So I think just getting to where we can use these line reactions and do our little, like fake mechanisms for these I think are really nice, because literally what you're doing is you're replacing whatever this side group is on the carbonyl. You're replacing an OR with an OH or an H2 or a Cl. Like that's kind of the big transformation that you do. So I think it's worthwhile to just kind of practice these with box problems. Maybe I'll say the general idea of the mechanism for all of these. So we call it a nucleophilic acyl substitution. So nucleophile comes and attacks our acyl group, which is when we have a carbonyl and a carbon on one side. We get to some intermediate here, and then we lone pair push off a leaving group, and now we've replaced what was originally there. That's the core idea. It's this with some acid-base steps mixed in. And to help you with all that, like I do have a reaction summary sheet again for this one. I'm not going to have reaction summary sheets for every lecture, but for especially these new ones, like the first few ones, I want you to kind of see and like have all the steps and have like a fierce resource for it. And so for the CAD reactions, I do list out like all the steps and everything. But let's look at these CAD box problems here. And these are from Skill Builder page 6, challenge problem 3, challenge problem 4. So I'm going to give you a few minutes. I would say don't do all of them. Pick like two or three, and try to do them. Also, I'm going to do a quick vibe check. If I went 10 minutes over today, but we could get a challenge problem synthesis done, would you want to do that? The alternative is we could just end at the normal time, and then in my other section, I will probably do it, and you could like watch the video. And so if you do want to head out at 10:30, you can. But if there are enough people that want to just get it done and do it together, we will do that. But I'll give you like 3 or 4 minutes to do some of these box problems.
Making pasta flesh. You never cook me sausage on an open flame. Never anoint me with oil. Never write me a novel. You never poison the mojitos
It will
of
be so
my
much more helpful if I just put up the.
enemies. You never make me a
Here we go.
marzipan.
So then you don't have to keep switching back and forth.
In a holy war. You never treat me like Oprah, never go supernova. You never animorph, transform into a cloud of bees. It's like you don't care. It's like you don't care.
A place in the city, a chair and a bed. I cover up all the mirrors I can see myself. I wear smoke like a wedding veil. Make a meal I won't eat. Step out into the street alone in the city. It comes over me, oh, I'm missing you. Yeah, I'm missing you. And all the things we used to do. MDMA in the back garden, block pupils up. Weekends for hours straight, oh baby, what was that? I remember saying that this is the best cigarette of my life. Well, I want you just like that. Into your hands, but in a sandstorm and it knocks me out. I didn't know then that you'd never be enough. Oh, since I was 17, I gave you everything. Now we wake from a dream. Well, baby, what was that? What was that? Baby, what was that? Do you know you're still with me?
That's why everyone's in section 9.
When I'm out with my friends, I stare at their painted faces that took color face. You had to know this was happening. You were feeling my heat. Went in the light down, baby, see right my face. Reality.
Hey, Triple C show work.
I tried to let whatever has to pass through me, pass through. But there's a stand while I know it might not let me go. MDMA in the back garden, blow pupils up. We kiss for hours straight, oh baby, what was that? I remember saying then, this is the best cigarette of my life. Well, I want you just like that. Into your hands, we're in a sandstorm and it knocks me out. I didn't know then that you'd never be enough. Oh, since I was 17, I gave you everything. Now we wake from a dream, oh baby, what was that? What was that? 'Cause I want you just like that. Do you like I can make it alright? What was that? Do you like I can make it alright? Baby, what was that?
Okay. So let's do some of these together. I'm going to go pretty quick on it, but I am going to do call and response, and I would love to hear sound when I ask a question. So we are going from a carboxylic acid to an amide. Are we going up or down in reactivity? Up or down in reactivity, carboxylic acid to an amide? We're going down in reactivity. Amides are less reactive than carboxylic acid. And if you look at the chart, amides are down relative to the carboxylic acid. Remember, this is organized, increasing reactivity. Okay, so if we're going down in reactivity, can we do that directly, or do we have to do more than one step? Directly. So we don't need these. If we look on the sheet, what we use is we use DCC and whatever amine that we're adding. How do we figure out what amine we're adding? We literally just chop off our groups. So we need to supply this thing right here, nitrogen in a 5-membered ring, but then we need to make it neutral, so we plop on an H. That's it. Okay, next one, we start off with an amide, and we go to ester. Are we going up in reactivity or down in reactivity? We're going up in reactivity, so where do we need to visit first? Carboxylic acid, Grand Central Station. So going from an amide to a carboxylic acid, I look up, okay, amide to carboxylic acid, that's H3O plus. Okay, and then carboxylic acid to ester, I need to do an alcohol and H plus. So let's go back and see. So firstly, H3O plus, that gets us to here. And then, okay, I need H plus and some alcohol, but to figure out what the alcohol is, all I do is I cut here. I see I have this that needs to be added. How do I turn this into an alcohol functional group? Well, I just add an H. So that is everyone's favorite alcohol, ethanol. Okay, here we're going from an ester to an acid chloride. Are we going up or down in reactivity? We're going up because remember, acid chlorides are most reactive. So if we're going up in reactivity, can we do that directly? No, we can go down in reactivity directly. We can't go up directly. So we need to visit Grand Central carboxylic acid. So ester to carboxylic acid, there are a couple ways that we can do it. One way that we could do it is with base, and one way that we could do it is with acid. I'm just going to use the base one, but you could do either one. So with base, you use NaOH, H2O, and H plus workup. And then carboxylic acid to acid chloride, and again, this is just looking up the reaction, like line reaction on the table. It's SOCl2. Down here, acid chloride. And then what functional group do we have over here? It's not a cat, is it? What functional group is this? She's just an amine. What type of amine is she? Primary, secondary, or tertiary? She's a tertiary amine. Good. Remember when I said we only know a few reactions in this entire class that make amines? And there's actually only one that makes a tertiary amine. That's being made from an amide. This is the only reaction in the entire class that can make a secondary or tertiary amine. So if we think about that, okay, I know that this had to have come from this amide. Is that fair? That we know that? And then our last steps are going to be lithium aluminum hydride with an acid workup. And that's going to do our amide reduction. So then our question becomes, how do we go from an acid chloride to an amide? Are we going up or down in reactivity? We're going down in reactivity. So what I'm going to do is I'm going to cut this off. And I know I need to supply that nitrogen as an amine here. And it's in a little 6-membered ring. And for acid chloride to amide, what we need is our amine, and we just write EX for having excess of it, or we do an amine with pyridine. The reason why we do that is in the mechanism, if you don't have an excess or if you don't have a base like pyridine, you're going to use up 2 equivalents of this for every one reaction because you need a general base for one part of it. So I just do the amine and pyridine normally. Slide. And then I'll do one last one. And to be so honest, I don't think I'm doing the synthesis with y'all today. I think that there would be too much to talk about all of the peptide synthesis and the synthesis altogether. I think it would be closer to 20 minutes beyond. And so I would say just check out the video, last 10 minutes of the section video that gets posted, and I'll be going through that. So sorry we didn't get to do everything today. Let's start off with carboxylic acid. And we see this girl DCC. If I go to my little reaction web, where do you see DCC here? Going to form an amide, right? And really what she does is she cuts off this, and then she plugs in an amine here, right? So let's go and see. It's this dicyclohexyl carbo diimide. Like, you don't know the mechanism for that one. So here, what we're going to do is we're going to cut off that OH, and we're going to put the nitrogen here, and she has 2 ethyls on her, like this. Or you could just write ET2, either way. So now we're at an amide. And then lithium aluminum hydride, does that do oxidation or reductions? Reductions. Hey, we just saw an amide reduction, and it took us to what functional group? An amine. So if I were to do a fake mechanism going from amide to amine, what would you tell me to do? Draw, erase, what? You literally erase the carbonyl, that's it. So you say, shh, you're gone. So what we're left with is this molecule, which is kind of fierce. Her name is triethylamine, because we have 3 ethyls and it's an amine. But her cousin is my favorite. So this is tetraethyl, and it's locked with a positive charge, and looks like a little dude dancing. So I call him the tetraethyl ammonium man, because he's just like, it's very like Keith Haring coded. Cool. So that's talking through most of the lecture 5 stuff. The stuff that we didn't get to was the amino acid synthesis. And this is just a type of synthesis, and you're going to have one of these either on exam 2 or the final. The nice thing about these synthesis questions when you get to it is you have to do all this protection and deprotection, and that can be like 6 of a 10-step synthesis. And so because you know these 6 steps always have to happen, there's like less crazy stuff that can be thrown at you. So it's a little bit more approachable. It looks a little scary. I promise that this stuff is actually a little bit easier. But thank you for coming to section. I hope it was helpful to get a start on some of this. Remember, tonight the quiz is due, the group exam is due, and there are not extensions on it, so make sure it gets turned in on time. Yeah, I'll stick around and answer some questions. But rest up this weekend. I know that this was like a big week with the exam and everything. But you're halfway through. Hey. Okay, have a good one. Yeah, see ya.